Here we're going to see the hydration of an alkene. Hydration means adding water. Where does the water come from? If this is an aqueous solution of hydrochloric acid, that means that it's mostly water. The acid just acts as a catalyst to get the reaction going. This hydration is an addition reaction. In an addition reaction, one thing adds to one of the carbons in a double bond, and another thing adds to the other carbon in the double bond. In this hydration, one carbon is going to get an OH, and the other carbon is going to get shafted, and it's just going to get an H. Which carbon will get shafted? We'll find out by doing the mechanism. And this reaction starts very similarly to the bromination reaction that I showed you guys in the last video. We have p electrons in the pi bonds. The pi bond is the second bond of the double bond, and the electrons are hanging out kind of away from the carbon-carbon double bond. So they are great nucleophiles. Give me just 1 second. I'm going to make this a better three-dimensional representation. There we go. You can imagine these dotted line hydrogens as pointing away from us into the computer screen. So we've established that there's an electron cloud below or above the carbons that is attracted to positive charges because it's a nucleophile. So what exactly is it attracted to in a solution of hydrochloric acid? Now remember, HCl dissociates into separate ions, so what you really have floating around is these hydronium ions, where because of bond polarities the hydrogens have a high partial positive charge. So what happens first is the pi bond electrons form a bond with a hydrogen in the hydronium ion, which is acting as a nucleophile. And the water gets released from that. So what is the result of these two electron movement arrows? Let's find out. Okay, we're not done yet, so don't get confused. But this is what we have so far. We know that the hydronium ion turned into a water. We know that if the pi electrons are no longer being shared between the two carbons, there's no longer a double bond. Because now, instead, those two electrons are being shared between a carbon and the hydrogen. Here's where the reaction starts getting different from the bromination that we saw in the last video. In the last video, the bromine added kind of to both carbons. It was bonded a little bit to both carbons. But in this case, the hydrogen doesn't make multiple bonds. So the hydrogen has to pick one carbon to get bonded to. And that's going to leave the other carbon SOL. If you don't know what that stands for, Google it. It's inappropriate language. SOL, in that it's going to be a carbocation. It's not going to have a full octet. Using what we know about carbocation stability trends, we should be able to figure out which carbon is more likely to be a carbocation and which carbon is more likely to grab the hydrogen. There are two choices here. There could either be a tertiary carbocation formed here, secondary, that would be secondary, or a primary carbocation formed here. And you know that primary carbocations are less stable than secondary or tertiary, and that molecules always want to be as stable as possible. So what we're not going to see is the formation of a primary carbocation. The way to avoid this primary carbocation is to have the hydrogen bonded to that carbon. And it would look like this. So this is the result of the first step of the mechanism. Those two electron movement arrows yielded this result. and this is called a carbocation intermediate. Any carbocation is a electrophile and pretty unstable, so it's going to react with the first nucleophile it finds, and in a solution, aqueous, it's going to find water. The lone pair on a water will bond to the positively charged carbon, and that will result in this. And this species is still kind of unstable, so it will act to get rid of its hydrogen. That hydrogen is going to get grabbed by another water, and the acid that started this whole reaction gets regenerated. And that's why the acid is called a catalyst. It is regenerated. And the product that we're really interested in is this thing, which is an alcohol because it has a hydroxyl group here. And it's really important to note that this is a Markovnikov product, which means the rich get richer. Here, the OH was added to a secondary carbon, and a hydrogen was added to the primary carbon. Because remember, this is where the double bond used to be in here. So what the rich get richer means is this carbon that was already bonded to two other carbons, it got another big thing bonded to it. But this carbon that only had two crappy hydrogens bonded to it, it only gets a crappy hydrogen in addition. And this was a Markovnikov addition, all because back here, when the molecule chose to have a secondary carbocation intermediate instead of a primary, it was that choice where the hydrogen decided to add to this carbon instead of this carbon.